Mechanical vapor compression reduces the energy used in the evaporation process by up to 90% compared with conventional systems. It works by reusing the heat energy contained in the vapor. This energy would otherwise be wasted. In a typical falling film evaporation plant, the feed liquid enters the top of a vertical chamber called a calandria. The liquid is dispersed across a large number of vertical tubes. As it flows downwards, it tends to form a film on the inside of the tube. Between the top and bottom sections of the calandria, there is a sealed area where the tubes pass through a jacket of high temperature vapor. This section acts as a heat exchanger. As the hot vapor condenses on the outside of the tubes, it releases latent heat, which raises the temperature of the feed liquid in the tubes. By the time the feed liquid leaves the bottom of the tube, much of the water has been evaporated off, leaving a concentrated, viscous liquid. The water which has been evaporated off leaves the tube as vapor. In the bottom section of the calandria, some of the concentrated liquid gathers and can be drawn off. The hot mixture passes into a cooler chamber called the separator, where more of the concentrated liquid falls to the bottom to be drawn off and the vapor rises to the top. This vapor now contains most of the energy that was initially fed into the system. The X-valve turbofan sucks the vapor from the separator and recompresses it, raising the pressure and so increasing the temperature to the point where the vapor can once again be used as a source of heat. The X-valve unit is an extremely robust, gas-tight turbofan ideally suited to the pressures, temperatures and volumes of the MVC evaporation process. At its heart is an ultra-high-speed impeller with a tip velocity of over 1,000 km per hour, faster than the speed of a jet airliner. The X-valve rotor probably has the highest tip velocity of any welded impeller ever manufactured. The reheated vapor can then be fed back into the calandria to provide the heat energy required to evaporate more feed liquid as it passes down the tubes. The mechanical vapor compression process is a highly energy efficient and cost-effective way of retaining and reusing the latent heat contained in the vapor, energy that would otherwise be wasted. Once the process has been started and brought up to temperature, the only energy input required is the electricity to drive the X-valve turbofan.